Good morning, my dear students. Here in this lecture video, I am taking another problem that is the problem number 4. Okay, so here the syllabus, that is what so far we studied about the problems on simply supported beam and the UVL, that is uniform distributed load. Okay, so here how to solve this point load with a roller support problem. Okay, so here this is also very important question. Okay, so problem number 4. So question is given like this: for the beam below shown in the below figure, so determine the deflection under the given load and the take Young modulus is equal to capital E is equal to 2 into 10 to the power of 8 kilonewton per meter square, and moment of inertia I is equal to 4 into 10 to the power of minus 6 meter m to the meter to the power of 4. Okay, so here in the beam problem, so all the questions are look like same only. Okay, so but the diagrams are different and the load which is acting on the given beam is different. Okay, so after reading the questions you need to calculate in the all the problem only the deflection only. Okay, so but the beams going to beams are different. Okay, so here the logics what is there means, here you have to first the Young modulus and moment of inertia have to convert into the kilonewton per meter square is there or not. Okay, so in this problem they given directly, so kilonewton per meter square and moment of inertia R is 4 into 10 to the power of minus 6 to the power of 4. Okay, so there is no need to convert here. Okay, so you need to multiply this into this EI. So EI is, if you multiply these two means you are going to get 800 kilonewton meter square. Okay, so here look at in the previous problem we solved what the beams with simply supported beam and uniformly distributed load with the two element. Okay, so that is, so here in this problem, so here the ruler support is there, this is the point load. Okay, so the only the beams are going to change, the questions remain same. You need to calculate in the all the problem only the deflection only. Okay, so but the beams are different depending upon this beam, you have to calculate the element stiffness matrix for different beam element. Okay, so look at here, the observe the diagram first. Okay, so here how many the wherever force is acting, their node will be present. Okay, so from this point to this point one element, from this point to this point second element. Okay, so you have to remember this. Okay, so for the first element length is given, how much length is given for the first element is equal to 5 meter and the second element length is given 5 meter. Okay, so total length is 10, so they only given the middle force. Okay, 10 kilonewton. So this force is given what, it is not a UDL force. Okay, it is not a P naught, so you have to take the direct in this problem F1 M1 F2 F2 M2. Okay, so no need to use the force due to UDL. Okay, so this is the 10 kilonewton. So from this point to this point length is given 5, this is called as element number 1. From this point to this point element number 2 length is given 5 mm. Okay, so the same, so here at node number 2 is what the this is ruler support. Okay, so I already told you in the previous problem we solved what simply supported beam, and one more is what uniform distributed load. Okay, so here in this problem, so one end is fixed, another end is what here ruler support is there. Okay, so in like that you have to solve the numerical problem. Okay, so here, so again same, the first step of finite element model is what, so comparing the given diagram you have to draw the free body diagram. Okay, so look at here 1 2 3, so right here draw the one beam element like this. Okay, node number 1, node number 2, node number 3. Okay, at node number 1 the V1 theta 1, so theta 1 is called as rotational degree of freedom and V1 is a translation, V1 theta 1 and F1 M1 force into moment. Okay, so similarly at node number 2 V2 theta 2 F2 M2, at node number 3 V3 theta 3 F3 M3. Okay, so from this point to this point length is 5 meter, from this point to length is 5 mm. Okay, so if you construct this element then a problem is very simple. Okay, so solving the problems is very simple. Okay, so look at this, at node number 1 completely fixed it is there. Okay, so here V1 theta 1 are going to become 0. Okay, that is V1 is equal to 0, theta 1 is equal to 0. Coming to the node number 3, roller support is there. Okay, so in the roller support, so vertical direction force will going to be what 0 will be there, so V3 is equal to 0, so you need to calculate theta 3. Okay, so from this diagram you need to calculate V2 F2 and V2 theta 2 theta 3. Okay, from the, okay, so you need to calculate the deflection. Okay, from this diagram. Okay, so look at, we have the formula what the element stiffness matrix for the beam element is, we have this formula K is equal to E by L cube. So already we derived this equation with help of what Euler-Bernoulli theorem or global Cartesian coordinate system. Okay, so since here L1 and L2 are 5 meter and Young modulus are same for the both the elements, so calculate the commonly EI by L cube is equal to substitute the Young modulus I and length Q value, so you are going to get the 6.4 value here. Okay, So this 6.4 value you can utilize to while solving the element stiffness matrix. Okay, so for the element 1 element stiffness matrix for k1 is equal to this, we calculate ei by l cube is equal to 6.4. so v1 theta 1 v3 theta 3. Okay, so length for the first element is what, 5 m meter given, so put here 5. Okay, 6 into 5 30. Okay, substitute 30 here like this. Okay, so 6 into 5, so substitute here 30. Okay, so after calculating the for element 1 and element number 2 stiffness matrix, so you write down you are going to get the two matrix. Okay, that is what here the degree of freedom will be there. So v1 theta 1 v2 theta 2 v1 theta 1 v2 theta 2. Okay, so this is belongs to the first element and this is belongs to the second element. Okay, v2 theta 2 v3 theta 3 v2 theta 2 v3 theta 3. Okay, so this is what the these are the two degree of this is what the degree of freedom varies element to element. Okay, so in the element number 1 up to theta 2, element number 2 theta 2 theta 3. How means, look at the diagram here. Okay, so look at here in the diagram. So element number 1 is from node number 1 to 2. So v1 theta 1 v2 theta 2, that's it. Okay, coming to the second element, v2 theta 2 and v3 theta 3, that we have to write here. Okay, so this is very important. Okay, so depending upon this only we are going to calculate the equilibrium equation, that is global stiffness matrix, that is k is equal to k1 plus k2. So since maximum node is theta 3 is there, 6 element, so you are going to get 6 into 6. Okay, so k is equal to 6.4 is common is there. So I already told you how to calculate this. Okay, so look at this 12. So this how to write at 12 means, this is the what is the node number position for this element. So v1 v1. Okay, look at the first row first column, that is here also v1 is there, here also v1 is there. Check v1 in the both the matrices. Okay, so v1 12, here not there v1. So 12 plus 0 is equal to 12. Okay, like that you have to calculate this, you have to form this global stiffness matrix. Okay, so after calculating this global stiffness matrix, go for calculating the nodal displacement vector. Okay, so displacement nothing but what, v1 theta 1 v2 theta 2 v3 theta 3. Okay, so global load vector is equal to what, so here completely fixed, so consider f1 f2 f3 f4 f5 f6. Okay, so here completely fixed, so consider 0. So minus force f3 is given here, look at in the problem. So this f3 is given towards acting downwards, so consider negative sign 10 kilonewton, that is minus 10 kilonewton. Okay, so here look at, if substitute here minus 10, so here force is not given, consider 0. Okay, so once if you calculate the nodal displacement and load vector, so you go for calculating the equilibrium condition. Okay, so already substitute the, you have the formula, what equilibrium condition formula, we have k q which is equal to f. So, okay, substitute the k value and q value in f value here. So f value substitute here, q value substitute here, k value substitute here. So after getting substituting, you are going to get this. Now you apply the boundary condition. So okay, so in this boundary condition, you come node number 1 and at node number 2 is ruler support is there. Okay, so here at node number 1 v1 theta 1 is completely fixed, so delete respect to row and column, first row first column. Okay, at node number 2 nothing is there. At node number 3, so vertical direction is fixed is there, so v1 theta 1 v2 theta 2, though this we have to delete the fifth column. Okay, so remaining you have to note down. So the remaining is 24 0 0 200, this 6.4 v2 theta 2. Okay, so theta 3 is also remaining. Okay, so that you have to note down in the next slide. Okay, remaining you have to write down. So v2 theta 2 theta 3. Okay, so again you simplify this. Okay, to 24 into v2 plus 0 into t2 and plus 30 into 0. Okay, so after solving this equation, you are going to get v2 theta 2 theta 3 is equal to v2 is equal to minus 0.1139 meter and theta 2 is equal to minus 9.765 into 10 to the power of minus 3 radian and theta 3 is equal to 0.03906 radian. Okay, so after like this you have to calculate the global displacement vector from the given two element. Okay, so like this you have to calculate what the, in this problem they are not asked what the maximum deflection, they are asking what they are not asking what the deflection at midpoint. Okay, so they are asking only the displacement at each node. So each node we calculated what, v2 theta 2 theta 3. Okay, so remaining this v1 and theta 1 and v2 which is equal to 0. Okay, so because it is completely fixed. Okay, so like this we have to solve the numerical problems on beam problem, that is to calculate the element stiffness matrix. Okay, for example in this problem also they are asking maximum deflection, means again you have to use the formula v is equal to h into q. Okay, so where h is equal to Hermite shape function, again you in Hermite shape function you have to substitute the all the values. Okay, so that is what the way to solve the elements, that is what the maximum deflection at midpoint. Okay, so like this you have to solve the numerical problems on beam element. Okay, so in the finite element model, by looking diagram only you have to analyze what to calculate, what to not to calculate. Okay, that is most important here. Okay, so look at here, this is just I am giving hint. So here this is the beam element. Okay, so here one end is roller support, this is what the fixed, here the roller support is there. Okay, so here completely fixed means I already told you in wherever fixed is there you have to delete the respective row and column. Okay, Okay, since it is belongs to the beam problem, so here v1 theta 1, so v1 theta 1 will become 0. Okay, this is the v2 theta 2, so here nothing is there. Coming to this, okay, so here v3 theta 3, so v3 you need to delete, so theta 3 you need to calculate. Okay, so like that you have to analyze first, okay, then you can solve. Okay, so that is the first step. Second point, what to remember means, so you have to convert given data into kilonewton per meter square, and moment of inertia is equal to 10 m to the power of 4. Power should be there in the both the given data, so that we can multiply easily. EI is equal to like this. Okay, so EI by LQ formula is there. First you need to calculate this EI. Okay, so you have to remember this formula first. That is what element stiffness matrix for this beam element. This is the point third formula. Okay, so if you remember these three formula, all those things and procedure how to solve, then you can solve the any type of problems in what FEM. Okay, so I hope you understand this different types of beam problem. Okay, third problem. Okay, thank you.